nanohub.org. Online simulation and more for nanotechnology.
Thank you for the organizers for this opportunity to speak today. I hope that some of the audience will find my journey of growing to the transitional metal chalcogenides useful. So I'm going to cover quite a bit of failures. As people who do growth, you get quite a products that are not as optimal, and then eventually the hope is that you don't get to where you want to. So first, just the sulfurization of MOS2 using moly oxide, moly trioxide, and sulfur. But I was always wanting to do large area growth of 2D films. So I started out by converting metallic films. It's a bad idea. Then we moved to converting metal oxide films, much better. And I learned that substrate, at least, mattered quite a bit on which you put the metal oxide films. And then you can do films, but you can also do wires, where you're starting with metal oxide wires, and then you convert it into the TMD nanowires. And if there's some time left, then I can tell you some of the properties that I measure using the materials that I grow. So we're very familiar with these type of images. In fact, Arend is one of the first people also started to grow MOS2. I remember Aaron telling me about this when I was at Stanford as a postdoc, and he was visiting, I don't remember when, why, but when Aaron was doing a postdoc with Jim Hone. So we know this reaction very well. One of the precursors you can use is metal moly trioxide. So you co-evaporate moly trioxide with sulfur, and then you get the moly sulfide. So one thing to note is that you can actually break this conversion into the steps. So swapping out oxygen with sulfur, and then indeed you can do the stepwise sulfurization. So we had a new graduate student who joined the group, so he was learning how to do this growth, and he was not loading enough sulfur, so he was always getting intermediate moly oxysulfides, right? So I just had him, he was a great student, so we just took a look at this stepwise sulfurization reaction. So let me just tell you how he did it. So we all know that it's very sensitive to the vapor pressure, right? It's very sensitive to the vapor environment. And because sulfur vapor pressure and moly trioxide vapor pressure is very different, and also the transport of these species are very different, just the minute differences of how you load your substrate can greatly affect, right? And since he was a starting graduate student, he's going through all of these things. So when Sam was mentioning how there are over 200 or about 200 parameters that you want to keep track of, definitely the positions of the substrate may be in the units of millimeters or sub-millimeters, X, Y, Z is important, as well as the weight of the precursors. So here, when you put the substrate a little bit to the right, what ends up happening is that there's a slightly more moly vapor. And then he would grow these crystals that are definitely not moly sulfide. And when you do Raman, it ends up, we can identify it as moly oxysulfide. And then when he then moves the substrate to the left, then you're not getting as much moly vapor. So in comparison to the sulfur, now you're creating a sulfur-rich environment so that you're going to get moly sulfide. So you can see these triangular moly sulfide flakes along with the moly oxysulfide intermediate products. You can sulfurize this substrate again. So here's the optical image of how they look like. So you can sulfurize this substrate again. So here was the moly oxysulfide substrate. We just stick it again into the furnace and anneal it again with sulfur vapor. Then you will consume, but without any other moly precursor. So you're going to consume your moly oxysulfide and make these moly sulfide. Okay, so here is now moly oxysulfide that is being eaten up, and in the nearby you're growing moly sulfide flakes. But the idea that I wanted to try was large-scale growth, right, and potentially high quality. So we started out by converting metal film. So this actually started when I was a postdoc in Chui's group. So we're converting moly and tungsten into moly sulfide, moly selenide, tungsten sulfide, and tungsten selenide. And all we're doing is heating the metal film or foil in the presence of chalcogen vapor. And you can do Raman, you can do TM, and then you'll know that this is you made the TMDs. And the reason why I like this approach was that you can use conventional lithographic tools to make metallic heterostructures. So here is just photolithography, wafer scale, centimeter scale, moly tungsten strips, right? Lateral heterojunction, and then you sulfurize it or selenize it, and it works. So here is the substrate where we had pre-patterned moly tungsten strips, and then we're just in one go doing a sulfurization or selenization, and you can see that we can make the moly sulfide and tungsten sulfide sulfurized, and here is the somewhat of a rectification behavior that you would expect. If you put the electrodes in the other direction so that the current is flowing parallel, then you just see an ohmic sort of a straight line. So, okay, so that works. This is in lateral heterojunction. You can also sputter deposit film on top of each other. So moly square and then tungsten square, and then you sulfurize it. It works again. And then here is the cross-section elemental mapping. I'm not showing sulfur because sulfur is everywhere, but tungsten sulfide and moly sulfide. From Raman signature, which I'm not showing here, it's not a alloy. It's not a ternary alloy compound, but rather you have a distinct moly sulfide and tungsten sulfide. I mean, that is not to say that right at the interface, they may mix a little bit, but just from the Raman signature, it looked like we're retaining the moly sulfide and tungsten sulfide. So you can convert metal films into metal dichalcogenides, and we can extend it to tellurize as well. So here's a tungsten film we're heating. Here's a tellurium powder that we use, and then we're flowing hydrogen gas. And we do this at the atmospheric pressure. And we think that the hydrogen reacts with tellurium to make hydrogen telluride, that is intermediate phase, very reactive. And we think that this intermediate gas phase reduces tungsten and then makes tungsten telluride. So this can work. So here is now different thicknesses of tungsten sputtered film after tellurization, okay? And you can do the Raman characterization, XRD, and then we see that this is a T sub D phase tungsten telluride. So this is all good, right? Like large scale, super simple, super straightforward. But the dirty secret is that it's polycrystalline. So here is the tungsten telluride. These are the nominal sputtering thicknesses of the 2 nanometer tungsten, initial starting point, 7, 10, and 30. But now this is after tellurization. So you can see that the grain sizes are at the nanoscale, 10, 20 nanometers, okay? So this is terrible for transport. If you want to do transport measurements, this is terrible. So why is that? How do we, yeah, this is terrible. And the other thing is that for thicker films, the layers are not laying flat, but they start standing upwards. And then this we knew from the beginning. So here, when we are sulfurizing or selenizing the metallic film, and then when you look at it from TM, what you see is that the molecular layers are standing vertically, not laying flat. So here's a 3-dimensional representation of the film. So again, this is not so good, right? If you want to do transport, because you're doing a lot of hopping of electrons through the van der Waals layers. But this is, from the growth dynamics, this was kind of interesting, because if you look at the our growth parameters, the growth temperatures, the pressures, the flow rate of the gases or the precursors, they're the same. They're very similar to growing horizontal flakes when you use, let's say, moly trioxide or moly chloride with sulfur. Similar temperature range, similar pressure range. So why is it that in one case, let's say in A, we can grow horizontally lying flakes, but in the other case, why are we growing vertically standing layers? So when we first started to do this, we thought maybe this was kinetics, because the sulfur has to start reacting with the metal, and perhaps diffusion of sulfur in plane in making the layers is much faster than trying to make the layers laying flat. So perhaps this is sort of the kinetics, the transport of the sulfur. So I decided to take a look at this a bit more carefully. So here, this is moly film, sputtered moly film, nominal thicknesses of 20 nanometers down to sub-nanometer. And then we just put everything in the same chamber. So one go synthesis of all of them just to make sure that the growth parameters stay the same. And what we see is that these vertically standing layers at thick films end up turning into a flat, nice molysulfide film. So what this means is that it cannot be some sort of thermodynamic energy, right? Because we're doing it at the same, so it's not a thermal energy, right? Because we're doing it at the same growth chamber. Nor is it the diffusion of the sulfur, really, because again, this is same energy, thermal energy. So to do this again, I guess yet again, we made tungsten film, but where we locally etched some area so that there is a height difference. Locally, some regions are 10 nanometer thick, the other regions are 3 nanometers thick. And then we sulfurized it. So the same result as the one that I showed in the previous slide. The thicker part, the layers are vertically standing. The thinner part, it's poly-crystalline still. It's lots of grains, but layers are at least laying flat. Okay, so the layers decide to stand vertically or lay flat. So at the end, what we think is happening is that the strain that gets built during the reaction dictates the morphology. So when you do co-evaporation of moly oxide and sulfur, you have the gas species that come down and condense on the substrate, right? And then you can grow flakes. If you have a thick film that is anchored to your substrate, even though the substrate is amorphous silicon oxide, as you are shoving now sulfur into your moly matrix, it needs to expand to be able to take the chalcogen atoms. And there is just no way to make these nice, thin, horizontally laying films because the volume expansion is too much. And then the film is anchored to your substrate. So for intermediate thin films, it makes these polycrystallines where layers are kind of laying disordered. But when it's really thick, it's much easier to freely grow upwards, right? Because vertically growing upward, there is nothing that is holding them from stopping them from growing upward. So we concluded that the direction of the layers, whether it's standing vertically or laying flat, has to do with the strain that builds during the expansion as the metal is being converted to the chalcogenides. Yeah. So that's sort of our journey about converting metal films into chalcogenides. The idea was good, and the idea was that if we can just react metals, we already know how to do large-scale heterostructures of metals, and then you can make a one-go sulfurization or tellurization to make heterostructure TMDs. Yeah, but it's polycrystalline, and if it's thick, you're gonna make the molecule layer standing vertically. But this idea, I feel like, has to work if your starting film is better than metal. So if you think that the strain is building because you're shoving sulfur into the positions that's not there, how about you starting with a precursor film that is a bit more porous, right? So we changed to moly oxide, right? So the idea is that oxygen leaves and then sulfur takes the position. So here is now aluminum ALD deposited moly oxide. We work with our collaborator Nicholas Strandowitz in Lehigh. So he's an ALD expert. So he's putting down X number of cycles of moly oxide very reproducibly on sapphire. Then we just do the same reaction, evaporate tellurium in hydrogen. So the initial thickness of your moly oxide is going to determine the final thickness of your moly telluride. So here, the number of cycles for the moly oxide was not enough to make a fully continuous bilayer moly telluride. So we have a little bit of pinholes. You can see it right here. But for the most part, this made a bilayer moly telluride. And initially, it makes the 1T prime moly telluride because it's tellurium deficient. But as we run the reaction longer, it then converts to 2H moly telluride. So here, this is after the conversion of 2H moly telluride. There's a lot of intensity variations and a low mag, sort of mid mag to low mag TM. And in the diffraction, it looks like there's two preferred orientations for the grain. Okay. And then again, this is ALD process. So you can do a large area film. These are different thicknesses of moly oxide. And then when you convert it, so you can see that the darkest one is the thickest moly telluride. And then the most faint one is the thinnest moly telluride. And here is the cross section. So we didn't have enough moly oxide to make a continuous monolayer tongue. Oh, sorry. Oh, this is moly telluride, so the title is wrong. So this is so we didn't have enough moly oxide to make a continuous single layer moly telluride. So you can see there's some moly telluride disconnected, and these are tellurium blob that is sitting on top. Bilayer moly telluride, 2 to 3 layer, 3 to 4 layer, and 7 to 8 layer moly telluride. So now we picked some number of ALD cycles, and then that's what it gave us. So now we know we have a better ideas of the number of cycles that we should use, right? So we've optimized our ALD growth, and we're redoing the growth to hopefully get 2, 3, 4 layer integer numbers. This growth is nucleation. You can pick your growth temperature so that it's nucleation limited, so that you can have large grains. So here. This is we've arrested the growth sort of early so that we can catch the nucleation of a 2H phase. We can catch the nucleation of a 2H phase in the presence of the 1T prime everywhere. So here these spots are 2H grains, and then the rings are 1T prime. Optically, so we let it keep growing. So here's another example. Optically, the 2H one is a little bit fainter. So here you can see it's about 1 millimeter, one nucleus growing out with a 1T prime that is a little bit darker. And then you can characterize this by using the Raman, because the Raman peaks are very distinct. So this was very good. And then this is just a simple looking at the resistance as a function of temperature using chrome gold as the contact. So this is 2H film. So there's an activation behavior as you would expect. Here, these are 3 different samples. As grown, 7 to 8 layer thick moly telluride. Now you etch it. If you etch it, there's a little bit of damage that you do. And then here's another thinner one etched. So the slope tells you sort of the alignment between your electrode, chrome gold, to your band edge. And the point that I wanted to make was that if you compare our slope to exfoliated moly telluride from bulk, it's pretty similar, at least the band edge, the position of the band edge using the chrome gold as the electrode. Okay, so it turns out that the substrate is very important. So here A and B is moly oxide, ALD deposited onto sapphire and then converted into moly telluride. Then C and D is the same ALD process, but done on silicon oxide, right? By same group. And then you see that when we tellurize it, then instead of forming a continuous film, we form islands. Okay, so this was very interesting. And we had a question as to whether this is because of the topology, like sapphire is so much flatter than silicon oxide, or whether this is due to chemistry. One is silicon oxide and the other one is alumina, right? So right now, we are repeating the same experiment, but with the third substrate, and that is alumina, amorphous alumina, deposited on silicon oxide. And then what we find is that chemistry is a lot more important than the topography, as in if we convert moly oxide to moly telluride, but on the alumina substrate, then we can have a very nice film. Yeah. Okay. So converting metal films, not so good. You want to convert metal oxide films, it works. At least for us, we find that having good substrate is important. So chemistry, either alumina or sapphire, is good. But you can extend this to now make wires. So here, we're making tungsten oxide nanowires, and then we're converting tungsten oxide nanowires to tungsten telluride nanowires using exactly same conversion reaction. So you don't want to do it too high because then you might melt your oxide wires. So, but as long as you screen for the temperature, here is now the tungsten telluride nanowires that we can grow. So the crystalline structure changes completely. So here is the tungsten trioxide nanowires, and then after the conversion, tungsten telluride wires. So another topic that my group does quite a bit is looking at topological nanostructures. And the point of topological nanostructure is that you want to enhance surface effects and you want to study topological surface states. But reality is that pretty much all materials, maybe minus graphene, oxidizes. So if you have a lot of surface, you have a lot of oxidation, which will degrade your transport. So here is the example. This is a very busy slide, but so we can make tungsten telluride nanowires. But if you just leave the tungsten telluride nanowires in air, there's a lot of oxide you're going to form. So here is now, so let's look at this is XPS. Here's a tellurium P for the tungsten telluride, and here is the tellurium oxide species that you will grow with oxidation. And what that means is that you can just look at this bottom plot. So when we do transport measurements, the resistivity that you can measure on the tungsten telluride flakes, right, versus our nanowires, the resistivity of our wires are much, much higher. And I think this is all due to the surface oxidation. So actually, I think all that is to say is that for a lot of wire studies, you have to spend time passivating the wires so that you don't have surface oxidation. Okay. However, some compounds are like magic, and then you don't have to worry too much about oxidation. So here, we're now making moly-phosphide. So we're doing a phosphorization. So we're again starting with moly oxide wires, and then we phosphorize it to make moly-phosphide nanowires. So the initial work came from Max Planck Institute, where they made a bulk moly-phosphide. This is a topological metal. What caught our attention is that moly-phosphide has a high carrier density and very low resistivity, pretty comparable to ruthenium. And that's important because semiconductor industry know copper has a dead end, and they're studying ruthenium as a potentially alternative metal that can perhaps replace copper. So these, the molyphosphide numbers are pretty compelling, comparable to ruthenium. If you compare molyphosphide to other topological compounds, you can see that the resistivity is fairly low and carrier density is high. So this is what industry people care. So we made it into molyphosphide nanowires. We also made it into these like terrible, super porous molyphosphide flake. So what surprised me about this device is that when we measure it, this is red, the triple R, so the resistance residual ratio is about 2. I thought that this thing was going to be insulating because it's super porous, grains are like 20 nanometers. I'm thinking it's oxidized. So this was very promising. And then now we're making nanowires, and then we're measuring the line resistance. Line resistance is the resistance per length as a function of the dimensions. And the numbers are pretty exciting. So that's actually my journey of converting oxide into tellurides or sulfides or selenides. And I have 3 minutes, so I'm going to just scroll super quickly the why I grow them. So one is, 2D material is all surface. You want to put molecules, and then it can change the properties. This idea is not new. It's been done from the single wall carbon nanotubes, right? But I might argue that experimentally, if you ask somebody, let's say this MEOID, how many electrons should MEOID donate to your MOS2, for example? I might argue that experimentally, we have a very poor handle on that calibration. You can do DFT calculations, and then you can know how many electrons MEOID should donate. But as an experimentalist, I feel like we should check and verify. So here are 4 different types of molecules we studied. Here's a redox potential. So the redox potential sort of tell you the donating power that you should expect, but they have different ligands, so they have different sizes, different structure. So we're making field effect transistors. You can measure the FET characteristics before and after the functionalization. And of all the characterization techniques that we tried, we believe AFM is the best to count number of molecules. But so if you want to know how many electrons should a molecule donate, you measure the number of you measure the change in the carrier density. That's straightforward. You just make a device, and then you have to count how many molecules you have. Counting how many molecules you have is actually not that simple. XPS or SIMS is too crude. And then you overestimate how many molecules you have. So AFM is the right balance because it's easy to do. So you can do many areas. So you have a statistically robust number for your coverage. And the spatial resolution is good enough that you can actually measure the molecular islands. So here are the different molecules. We tried 5 different molecules as a function of different functionalization conditions. And then we do a whole lot of AFM to calculate the surface coverage. And at the end, the 2 numbers we got, one is for this particular compound that we call DMAP-OID. It donates, depending on the configurations, about 0.6 to 1.2 electrons in good agreement with DFT. And for this particular molecule, 0.24. So these are the experimentally measured or calibrated numbers. I don't have time. Well, in the 10 seconds I have, another one that I do a lot is intercalation. I like phase transition induced by intercalation. Graphene, there's a lithium staging that happens as you put lithium at the beginning when it's diluted, randomly distributed. But as you put more and more lithium, it goes through these order staging. And then we looked so we made a micro device and we looked into how these stagings get affected by strain. So what we did is that we looked, so when the staging happens, the first order staging, your Raman peak for the graphene splits into two peaks. So we basically follow that peak splitting as a function of thickness and at the electrochemical voltage at which that splitting happens. And you can see that the splitting happens at different electrochemical voltage, meaning we have to actually drive it much, much harder for thicker graphite, for thicker samples to make this staging happen. And all of the story short, at the end, what we think is happening is there's a local strain that builds, which is proportional to the thickness to the power of 3. And that actually adds a local nucleation barrier for the order stage to nucleate. Because if you actually calculate the strain energy, that strain energy is minuscule compared to the electrochemical energy that you have to provide. Therefore, it can only be some sort of activation barrier type number. We repeated the same thing for the heterostructures, looking at the phase transition of MOS2, but encapsulated with HBN. So that's that. The work was done by many students. Most of them are actually no longer in the group. They've graduated and started to do postdocs, and also went ahead and got industry jobs. But for the synthesis, I really have to acknowledge my collaborator, Nick Strandowitz at Lehigh, who's now providing me with the oxide films. And bulk of the work that I showed today was done by previous postdocs, Eric and Jay. Thank you very much.
Thank you, Judy. It's really too bad that we can't have like actual applause in these webinars, but that was a very nice talk. Thank you. Looks like we have a couple of questions in our Q&A. First question is from Pin Shane.
Hello. Yeah, so thanks, Judy. That was a very nice talk. You know, the TM image of your W at TE2 from the top down are really interesting. There's a lot of contrast in both in the atomic resolution image and then the lower mag.
Yeah.
Yeah. What is all this coming from? D and G? Quite striking.
I send samples to you if you want to look at. Okay, that's a good point. So when we were getting this reviewed, actually the reviewer commented that the inset in D is a diffraction pattern that we got, right? And then if you just kind of look at it by cursory look, it kind of looks like there's 2 grains. Yeah. But the reviewer was arguing that it's not a point, but maybe it's a little bit of an arc.
Oh, I'm not sure I agree with. Well,
so that was so. I mean, I guess I cannot refute that.
There's a little arc there, but I think your image G is very interesting because the defects almost look ordered.
So I give you the sample.
Okay, I give you my address.
Okay, great. Yeah, that's great. Yeah. So this one, so if anybody know how to get the film off of sapphire, please let me know. So for the plan view, these were grown on sapphire. No, these were grown on silicon oxide so that we can take them off from the substrate. So actually the film quality for D to G is not as good as the ones grown on sapphire. But we did it because we want to do plan view imaging. Yeah.
Okay. For our next question, we have Lei Lo.
Hello, Prof. Judy. I'm from NUS Singapore. I have some technical question on the sample transfer. So I would like to ask, is it very difficult to transfer the vertical standing TMDs onto TM substrate as opposed to the conventional laterally grown monolayers? Because I would assume that the area of contact of each of these vertical monolayer is much lesser than the wholly overlapping laterally grown monolayer. Yeah, that's my question.
Yeah, thanks for the question. So when we sputter deposit the metal films on silicon oxide, and then we convert it into the vertically standing TMDs. So as long as we dip the whole substrate into either HF or KOH, then the film float up. So whether it's more difficult or not, we don't know in terms of energetics, but in the lab, when you go do it, it seems pretty straightforward and we don't have much difficulty.
Okay, thank you very much.
Okay, our next question from one of the raised hands is Abdulali Fargi. Go ahead and ask your question.
Yes, please. Just my question is, how could you ensure good metal contact on your TMD deposited for transistor application? And how could you ensure the only contact or short contact?
Oh yeah. That's a great question. So anybody who does transfer measurements of nanoscale materials, the thing that you spend the most time is what kind of contact you have, right? So actually, right now, I mean, we etch away the contact area before we deposit metals, and then we do a bit of etching tests to make sure that we feel we've gotten rid of a lot of oxide, and then after that, you can do for some of the films, we've also done TLM patterns, for example, where you do a 4-point versus 2-probe. To kind of get it and have a gauge as to what your contact resistance might be. For now we etch. We do dry etch before we put down the metal contact.
Using dry etch. Okay, thank you.
Okay, we have time for one last question from Wilson Merchant. Go ahead and ask your question.
Hi, this is Wilson Merchant. Thank you for the nice work. I have a question. You mentioned that you're doing this in CVD, and then how sensitive is the synthesis process by just moving the sample to be around. So how do you control the flow rate of the argon if it's that so sensitive, so that your experiments are reproducible? And another one is, how do you also control the number of the layers? You talk about the different type of layers of molybdenum telluride. So I'm wondering, how do you control that? And also, what is the time of your experiments? Seconds, minutes? Can you please elaborate on that? Thank you.
Oh, the growth time? Okay, so for here, for this growth, where we have already a moly oxide film on sapphire, and then we're converting into telluride, for example, where exactly we put the substrate is not. It doesn't matter so much, because this is at the center of the tube furnace. We have a 2-zone furnace, and then you have coils, right? So we're putting it at the center, so it's pretty uniform over a fraction of the coils in the center, and it's not as sensitive to the pressure as well, because this is actually like almost atmospheric pressure, and we are flowing 100% hydrogen. There's no argon mixed here. When we convert the films, it's much more robust. The growth product is much more robust to the growth parameters compared to if you're doing co-evaporation of metal precursor powder with chalcogen powder. But here, as long as you just like load up with chalcogen, right? You like 1 to 300 sort of weight ratio, 300 being the chalcogen, then usually you can just reproduce it fine. But it's still sensitive to the flow rate, and also the pressure. But that's another thing. I feel like every furnace has its own sweet spots, and that the maximum number, like 20 SCCM. 20 SCCM for me may be very different from 20 SCCM for somebody else, depending on the furnace setup and everything else.